Hi, welcome to class. My name is Don LaFont, Professor Don, and this week in our A plus software class, we are covering the second part of networking. We're going to talk about the models, the OSI model and the TCP/IP model, and a little bit about MAC address layer and IP addressing. So let me go ahead and share my screen. And we're just about there. Yeah, I've had to re-record this presentation, so I don't have any students with me right now. But if you're watching this as a recording in our Netacad classroom, please ask in the help discussion forums. And if you are watching out on the internet, on YouTube, please ask your questions down below in the comment section. Please also like and subscribe to my video, and you'll be notified if you click the notification bell. You'll be notified when I release additional A+ videos moving forward. I also am getting ready to start releasing some Cisco 3 classes, so you can look forward to that as well if you're really into networking. All right, let's go ahead and get started. So Chapter 3, Part 1. Now, this is actually uh, one chapter that we're dividing into three different presentations because networking is such a large topic. And this is from Cheryl Smith's Complete A+ Guide to IT Hardware and Software. I've also borrowed some information from my previous courses. As you know, I'm a networking teacher, as you can see from my videos. I'm a networking teacher, so I have a lot of content that I have borrowed from to help this presentation be a little bit more informative. The presentation covers being proactive. Oh, I started at the beginning. Hang on just a second. That's the slide we started with last week in the previous presentation. Haven't seen that yet? Go watch it now. It'll give you a good introduction to this presentation. Now, this presentation, I actually have a couple of videos that I'm going to show you that are going to be really helpful for you to understand the concept of networking. Yes, we have all plugged, obviously, you're online, right? So we have all plugged in a router and a computer to a router and a router to the what the your ISP gave you. Maybe you have a fiber box like I have. And so we've all done some networking. You probably can use your laptop anywhere in your home, or your phone can connect to your Wi-Fi at home, and you've probably done that. But really what happens when you click on a link in a web page, what actually happens, right? How does the internet work? Well, there's a video that I found when I took this course about 9 years ago. That I found that was just impressive. The teacher played just a little snippet of it, but I really think this video is worth playing all 13 minutes of it. Now, the video is called Dawn of the Net, and you can find it on YouTube. I'm just linking off to your channel. I'll show it to you. And I can't and I understand this video looks old. It's from the 80s. The network hasn't changed that much since the 80s. Yes, we have yeah, yes, we have eliminated hubs and now for the most part, and we use switches. And in this video, they call the router switch. That's just a switch. But now that we just call it a switch. Now, all those switches can be smart switches and can have routing capability, but that's not really what they're talking about. But anyways, this video is going to take you on a path through the network, showing you what happens, but in a in a comic type of way, in a simulated pretend way. Obviously, the real internet is just made of ones and zeros, so this isn't real the way they interpret it, but it is a great way to explain what happens all the way through the process, all in the drop of a hat. We'll see that here. Let's watch the video.
For the first time in history, people and machinery are working together, realizing a dream, a uniting force that knows no geographical boundaries without regard to race, creed, or color. A new era where communication truly brings people together. This is the dawn of the net. Here, begin your journey into the net. Now, exactly what happened when you clicked on that link? You started a flow of information. This information travels down into your own personal mailroom, where Mr. IP packages it, labels it, and sends it on its way. Each packet is limited in its size. The mailroom must decide how to divide the information. Now, the package needs a label containing important information, such as sender's address, receiver's address, and the type of packet it is. Onto the internet. It also gets an address for the proxy server, which has a special function, as we'll see later. The packet is now launched onto your local area network, or LAN. This network is used to connect all the local computers, routers, printers, etc. for information exchange within the physical walls of the building. LAN is a pretty uncontrolled place, and unfortunately, accidents can happen. Packed with all types of information. These are IP packets, no packets, Apple Talk packets. They're going against traffic as usual. The local router reads the address and, if necessary, lifts the packet onto another network. Well, seemingly disorganized world. Conservative and sometimes not quite up to speed. At least he is exact, for the most part. The packets leave the router. They make their way into the corporate intranet and head for the router switch. More efficient than the router switch plays fast and loose with IP packets, deftly routing them along the way. Digital pinball wizard, if you will. Arrive at their destination. They're picked up by the network interface, ready to be sent to the next level. In this case, the proxy. The proxy is used by many companies as sort of a middleman in order to lessen the load on their internet connection, and for security reasons as well. As you can see, the packets are all of various sizes, depending upon their content. And looks for the web address or URL. Depending upon whether the address is acceptable, the packet is sent onto the internet. Some addresses which do not meet with the approval of the proxy, that is to say, corporate or management guidelines. These are summarily dealt with. Have none of that. For those who make it, it's on the road again. Purposes. It prevents some rather nasty things from the internet from coming into the intranet. And it can also prevent sensitive corporate information from being sent onto the internet. The firewall, a router picks up the packet and places it onto a much narrower road, or bandwidth, as we say. Obviously, the road is not broad enough to take them all. You might wonder what happens to all those packets which don't make it along the way. Well, when Mr. IP doesn't receive an acknowledgement that a packet has been received in due time, he simply sends a replacement packet. You're now ready to enter the internet, a spider web of interconnected networks which span our entire globe. Here, routers and switches establish links between networks. Now, the net is an entirely different environment than you'll find within the protected walls of your lab. Out here, it's the Wild West. Plenty of space, plenty of opportunities, plenty of things to explore and places to go. Thanks to very little control and regulation, new ideas find fertile soil to push the envelope of their possibilities. But because of this freedom, certain dangers also lurk. You'll never know when you'll meet the dreaded pain of death. Special version of a normal request ping, which some idiot thought up to mess up unsuspecting hosts. The paths our packets take may be via satellite, telephone lines, wireless, or even transoceanic cable. They don't always take the fastest, shortest route possible. We'll get there. Eventually. See, that's why it's sometimes called the worldwide wait. But when everything is working smoothly, you can circumvent the globe 5 times over at the drop of a hat, literally, and all for the cost of a local call or less. Near the end of our destination, we'll find another firewall. Depending upon your perspective as a data packet, the firewall could be a bastion of security or a dreaded adversary. It all depends on which side you're on and what your intentions are. The firewall is designed to let in only those packets that meet its criteria. This firewall is operating on ports 80 and 25. All attempts to enter through other ports are closed for business. E5 is used for mail packets. 80 is the entrance for packets from the internet to the web server. Inside the firewall, packets are screened more thoroughly. Some packets make it easily through customs, while others look just a bit dubious. Now, the firewall officer is not easily fooled, such as when this ping of death packet tries to disguise itself as a normal ping packet. Lucky enough to make it this far, the journey is almost over. It's just a line up on the interface to be taken up into the web server. Nowadays, a web server can run on many things, from a mainframe to a webcam to the computer on your desk. Why not your refrigerator? With a proper setup, you can find out if you have the makings for chicken cacciatore or if you have to go shopping. Remember, this is the dawn of the net. Almost anything's possible. The packets are received, opened, packed. The information they contain, that is, your request for information, is sent on to the web server application. Cell is recycled, be used again, and filled with your requested information. Rest and sent out on its way back to you. Back past the firewall and on through to the internet. Through your corporate phone. Onto your interface. To supply your web browser with the information you requested. Pleased with their efforts and trusting a better world, our trusty data packets ride off blissfully into the sunset of another day, knowing fully they have served their masters well. Isn't that happy ending?
So I love this video because it puts the internetworks and our communication across them in a way that anybody could understand. My wife, the English teacher, could probably understand that video and what happens in the video. That's a great starting point if you know nothing about routers and switches and IP addresses and MAC addresses and servers and hosts and all of the things that we're gonna learn a little bit about in this class. But then you're gonna go on, if you decide to go into networking, you'll have spent plenty of time working on those topics. Then I left this up here for a moment so you would see the dawn of the net, how the internet works. It's been here since 2011, but at some point in the video, it actually has a date of creation back in the 80s sometime. So this video has been out there for a long time. Visit it, give it a like, and I hope it stays out there because I use it every semester when I teach networking. Now, when we're talking about that path from when you click on the web to the application server on the other end, the web server that has the information that you're looking for, and then it reverses and comes back, that is the network. That is the internet. That is what you will be working on if you decide to go into networking. That's what this chapter is about. It's about networking. And to understand the different layers, the different pieces of networking, the International Organization for Standards, the ISO, developed a model for networking communications known as the OSI model. Now, it stands for Open Systems Interconnect model, but you will never see anybody call it the Open Systems Interconnect model. So you always call it the OSI model. It is a standard for information transfer across the network. The model sets several guidelines, including how different transmission media are arranged and interconnected. It talks about the how network devices that use different languages like Mac, Linux, and PCs all communicate with each other over this thing we call the internet. It talks about how network devices contact another network device, how and when data gets transmitted across a network. For example, when we're talking about wireless, when the send and receive is made on a wireless network, how data is sent to the correct device. How does a packet get from one side of the country or one side of the world to the other side of the world? How does it do that? That's called IP. IPv4 and IPv6 currently. How is it known? How it is known if the network data actually was received properly on the other end. So that's just a whole lot of words to most of you. So let's put it in a format that you can understand, the OSI model. Now, there are 7 layers of the OSI model. Now, these 7 layers each do a different thing. And they're all interdependent. So the physical layer, for example, has fiber and copper and wireless. If we came up with a new transmission medium, I don't know, telepathy, it would fit on the physical layer, okay? And it would have to meet the criteria of the physical layer. But for now, it's just fiber, copper, and wireless. The data link layer, that's MAC addresses. That's hop to hop. I always like talking about the post office and how you put an envelope in the mailbox in one side of the country, and on the other side of the country, grandma receives it a few days later. How does it get from the post office, from the mailbox to grandma's mailbox? Well, it goes from post office to post office to plane to the plane lands to post office to truck to post office to ultimately the post office that your grandma is at, and then it gets delivered to her street and then her address. That's the data link. Hop to hop to hop, all the way along the internet. We use MAC addresses of every unique MAC addresses of every device connected to the internet. That's the data link layer. We call it layer 2. Layer 3, that's IP, IPv4 and IPv6 at this point, and we'll talk about that in a few slides. But IPv4, 4.3 million addresses, 32-bit, 32 bits, ones and zeros divided into 4 octets. We have the network address and the subnet. That's all IPv4. IPv6, 128. We have 8 hextets. Let's see, we have 340 undecillion addresses. And it is, what else do you want to know about IPv6? Enough addresses in IPv6 to fill the universe from the sun to Saturn with 1-inch marbles, each having its own address. Anyways, 65,000 networks of 18 quintillion addresses. That's what we're talking about with IPv6. Currently at the network layer, we really only work with IPv4, IPv6. All you need to learn about in CCNA, because those two are the big networks. Yes, there's Novell, and there's Apple Talk, but the other ones aren't used much anymore, and we really use IPv4, IPv6 at this point. Transport layer, that's TCP and UDP. TCP is connection oriented, which means that a connection is established on both sides. They communicate with syncs and X, and anyway, they communicate. They set a connection. Once they have the connection, then the communication happens, and then once it's done, they finish the communication. Now that's TCP, and that's great for things that are important for like secure transmission of information, like your banking, for example. But it's a little slow with all of the conversation that needs to be established first. So there's UDP. UDP doesn't have all those layers of communication. It's connection less. TCP is connection oriented, and UDP is connection less, and that means there's no connection. It's just sent. It's like FM radio. FM radio, it sends a signal. If you got your FM radio on in your car, you will hear FM radio. If you don't, then it just doesn't get listened to, right? UDP, it's for things like VoIP, anything that needs fast times. And if you lose a little bit here and there, it doesn't matter. If you're talking to somebody on a VoIP call and you lose the connection for a moment and you miss a word, you just say, hey, can you say that again? I lost you for a moment. Not a big deal. Do that with a banking transaction, all of a sudden the money disappears. That's bad, okay? So we want TCP for banking, UDP for YouTube. Actually, YouTube can be both, but VoIP is a good one for UDP. That's transport. Transport also is in charge of breaking up all of the packets and labeling them to make sure that you have the segments, and the segments all are numbered. And because we don't send one big file over the internet, we send smaller files that are mixed up as they get sent through the network. And then when they get to the other side, they're all put back together again. TCP, not necessarily in UDP. Session, I like to think of the session as a communication guard, if you will. So think about when you sign on to your bank or the college. After a little while, it gives you a warning that they're about to disconnect. That's the session layer. The session layer is in charge of maintaining a communication and ending it if nobody is communicating anymore. Otherwise, you'd have all these open transmission, all these open TCP connections where nothing's actually happening, taking up bandwidth and resources. So the session layer is important with controlling the communication. It also has something to do with packet data being broken up into pieces too, but mainly handling the session. Presentation, just like it sounds, it's in charge of presenting the data with JPEGs and with MP3s, MP4s, BMPs. How is the data going to be displayed at the application? So application layer, anything that uses the internet that interacts with the web. So for example, Paint does not. So even though Paint is an application, it's not. It doesn't use the OSI model, because you mess with Paint on your own computer, it never goes anywhere. But an application such as a website, HTTP, or email, or FTP, all of those are applications that send and receive something. So let's go back to HTTP, your website or your secure website with HTTPS. Presentation layer would be responsible for presenting the data or preparing the data for being presented at the application layer, and then the application layer is actually the program that the user interacts with. I hope that helps. There's a way to remember these over here. There's one way to remember it going down. I don't know that way. Some people do. Something about all something people do this. All people something or other. I don't know. But I know about pizza. I love pizza. So I know the other way. So the other way is, please do not throw sausage pizza away. Please do not throw sausage pizza away. Please do not throw sausage pizza away. Why would you ever throw sausage pizza away? Pretty easy for me to remember. And where you use that is when you go into an exam. You have a blank piece of paper, and that's all you're allowed. And you take a pen and you write PDNTSPA. Please do not throw sausage pizza away. And then next to it, you write physical, data link, network, transport, session, presentation, and then put the numbers next to them, 1, 2, 3, 4, 5. And so you're going to answer a whole bunch of questions just by having that written down, because it's going to ask you at what level, at what layer does this happen? At what layer does that happen? And once you learn it happens at the data link layer, that's switches and MAC layer, then you answer those questions. Your network, and this is IP. You answer anything dealing with IP is at the network layer. And these layers are not real. They're just conceptual layers. So for example, the network layer, that just represents IP, and so it's IPv4, IPv6. What if we came out with another IP, maybe IP10, using neural networks, right? And it's a whole different way of sending addressing at the network layer. So we have to be able to address neural networks in, I don't know, biological computers. They must be working on it someplace. I don't know. Biocomputers with neural networks. That sounds scary if you ask me. But anyways, that would you have. I don't know. I don't even want to think about that. But the network would maybe IPv10, right? And it's a completely different way of addressing than IPv4 and IPv6. So layer can't really interfere with any of the other layers. You may, if we do neural networks with, say, a brain-like computer, the physical layer obviously has to be changed because you can't have ones and zeros. We'd have to have something else that's. But anyways, you get the idea. It's all just symbolic. This is what happens at this layer. This is what happens at this layer. We're going to learn in a few minutes that we also have another network called TCP/IP, another model, I should say, TCP/IP. That model covers the same 7 layers here, but it does it in 4 layers. NIDA is how I remember that one, and I'll show you when I get there. Let's keep moving. So what happens at the OSI model is we have data that streams from the application. It streams down, and here it's put into the right format, and here it is at the session layer. It's open communication if required. Also a little bit of division there. Segments broken up into pieces, and each one's called a segment, and it's all addressed and numbered, I should say. A packet, this gives an IPv4, IPv6 address is assigned to a frame, a MAC address is assigned to it. All these headers are added to it. Ultimately, a whole bunch of ones and zeros making up the frame get down to the physical layer. And whether we're talking about fiber, where lights flash on and off way faster than you can see, but light being transmitted as ones and zeros, or copper voltage, or wireless RF, we're talking about ones and zeros being transferred across the medium to the other side, where this is called encoding. When it gets to the other side, it's called de-encoding, or de-encapsulating. This is encapsulating on this side, de-encapsulating on this side, or just decapsulating. I've seen it both ways on the internet. So I actually have a video that shows you this. This video doesn't show you on the OSI model. It shows you on the TCP/IP model. The same thing. The application is just the top 3 layers. The network is both data link and physical as a network. And then these two this is the network layer and that's the transport layer. So it represents the same communication. It just does it in a smaller 4-layer path. Now we, as learners, we talk about addresses and layer 3 IP addresses. That's not true here. It would be, well, layer 1 and layer 2. But we don't talk about this in school. We do know about the TCP/IP model, and out there on the internet, it's the suite that is normally referred to. We're talking about TCP/IP in networks. This one officially, I guess, won the competition. But in school, we talk about OSI model, and this is how we actually learn. If you go on to take my Cisco class or watch any of my videos, we learn this is 1 week, and we learn about the data link layer the next week, and then we learn about the IP networking layer the following week. It's not exactly like that, but that's how we learn. This would be a short course. It'd only be 4 weeks. I have this video, though, that I love watching. It's one of my favorite educators online. His name is Astrid Carnici. I highly recommend this man. He knows way more about networking than I do at a much deeper level, and I highly recommend him. Sometimes this can go over your head, though. I hope I'm right in the middle. Jason E. Johnson, I also respect as an educator as well. He's great for introduction. I think I'm in the middle, and then Astrid Carnici is when you want a deeper dive into any concept. Now, you're like, what? 11 chapters? Wait, we have, I thought you said networking had 16 chapters, right? Well, this is CCNA v5. Networking hasn't changed. Just the way we teach it has changed. And in the way we taught it back in CCNA v5, Astrid in chapter 10 created this video, and I love this video, but he waited until the end of his class to put it all together. Now, I don't believe in that. I believe you should introduce your students to the concept so they know where to place things, and then teach it to them. And then at the end, say, see, this was easy, and show it to them again at the end of the semester. So here, I'm going to play this video. It's only 5 minutes long, and it's an awesome video again. Astrid Carnici.
Hey, my name is Nichi of CCNA, CCNP, Cisco Trainer. Now we're going to move to section 3, the message heard around the world. Now, what happens to sensor network? We use a browser or email or FTP server. That message is going to go through the layers. At each layer, there's something going to happen. An application layer is going to identify what kind of message is it, what stream is it, how am I going to compress it, how am I going to format it, and so on. After the application layer is actually done with the stream, it's going to hand it over to the transport layer. Now, the transport layer, the message of this layer is called a segment. The transport layer is going to do is going to take this message and it's going to split it on a different segments. While it's splitting in the segments, is going to identify each segment with a sequence number. So each segment is split into pieces, and each piece is identified with a sequence. The transport layer is going to add its own header. Its header is a port addresses. So it's going to take the source port is going to take from range. In this case, I've used 64,001, and then destination port 80. Port 80 is well-known range, which identifies that this message is the destination is some website, HTTP. For example, if we were using secure HTTP or HTTPS, the destination here would be 443 and 480. Okay, after the segment, transport layer has finished having his own header, is going to pass it through to the internet layer. At the internet layer, it's called a packet now. Now, internet layer is going to add its own header. The internet header is the source IP address and the destination IP address. So the source IP address is 10.110, which is the client PC on the top, and the destination IP address 10.1.120, which is the server on the. Now, this source and destination IP address, it never gets changed from the source to the destination. Doesn't matter how many hops it goes through, the source and destination IP address remains the same. After that, and now it's called the packet. After the internet layer is finished, it's going to give it to the network access layer. At the network access layer, the name changes. Now it's called a frame. At frame, it adds the MAC address, source MAC address, and destination MAC address. Plus, it adds the frame check sequence to make sure that the frame has not been. The other side actually knows it's going to check the first thing, frame check sequence, and making sure that the frame has not been corrupted on the transit. And the source source MAC address and destination MAC address would change hop from hop basis. Okay, the network access gives it to the make sure they're all zeros and ones, and it passes this through the medium, and it goes to the destination. But the destination is going to do the reverse. When the client was packaging this with the different headers, data, it's called encapsulation. Now, when you go to the other side, the destination is going to do something called de-encapsulation, which is going to mean it's going to open and remove all the headers. Okay, let's go again. The other side. Next, it's going to go to the network access, open the frame, which is called now. And first thing it's going to do is going to remove the frame check sequence, making sure the frame has not been corrupted on the transit. After you make sure that the frame has not been corrupted, it's going to read the source MAC address and destination MAC address. Let's find out the destination MAC address is itself. So it's going to pass it through layers now. Remove that portion of the header, and it's going to reach the internet layer. At this layer is called the packet, and this packet is going to read the source IP address and destination IP address. Well, really just destination, making sure that it's for itself. If it's for itself, it's going to remove the header and give it up to the layer, which is the transport layer. Again, this layer is a segment. So segment is going to make sure that, okay, this is the destination is 80, which means that they're talking about HTTP. And it's going to make sure that all the segments arrive and it puts them on the correct order and then give it to the application layer. The application layer is going to hand it over the stream to the destination. Okay, so this is how the packet travels from the source to the destination. When it gets to the destination, the destination, if it has any messages to send back to the client, it will actually, the process will just be that, the opposite we just saw. Okay, thank you for watching my video. This has been a Nishi. Please have a look at my other videos and don't forget to subscribe. Thank you very much.
Again, I highly recommend it. Astrid Konichi. I think he's an awesome instructor. When you get to networking, whether you take me or somebody else, make sure you remember him, follow him, and hopefully he and his videos will be useful for you to learn networking. So let me close out of there. All right, so let's keep going. So he used the TCP/IP suite. But the same thing can be done with the OSI model. It just has more layers and what happens at each layer. But you can understand all of these headers are all stripped away ultimately from the stream of data that's originating. By the way, Astrid does misspell the word spelling for stream. It is STEARM. I'm sorry, STREAM. Not the way he spelt it. I'm not sure why he spelt it that way, but who knows? Maybe wherever he is, that's how you spell stream. I don't know. But it's spelled normally, like a river is a stream of data. And here they're showing the same thing with the addition of adding information, encapsulating as you move down, de-encapsulating or decapsulating on the other end. And I also want to mention that all of these segment, packet, and frame, these are all PDUs. PDU stands for Protocol Data Unit is a PDU. And a segment is a PDU, a packet is a PDU, and so is a frame. So don't get confused by that. They're all PDUs. They're just different named PDUs. The TCP model today is the most common network model. It exists to explain the same network layers as the OSI model, but it does so with fewer layers. The same concepts of networking, just with fewer layers. The TCP/IP protocol suite consists of many protocols, including transmission control protocol. I was talking about that earlier. Internet protocol, IP, dynamic host configuration protocol, 8DHCP for handing out IP addresses, file transfer protocol for transferring files, hypertext transfer protocol for websites. So, and all of the other protocols that we use on the internet that are not mentioned. These are just a few of what the examples that they're given in the chapter. Now we're going to talk about layer 2 and layer 3 addressing. Now the MAC address, this is layer 2. Network adapters normally have two types of addresses assigned to them. The MAC address, layer 2, is a 48-bit unique number that's burned into the NIC, burned into the chip. And that address is unique in region. I used to think it's unique in the world, but I've been taught that different regions, like the Asian Asian Pacific region, European, African region, and the States, North America region, they can have duplicate MAC addresses because the physical address in IPv4 especially, but it also works for IPv6. But the physical address for IPv4 just has to be unique locally because we'll learn in a couple moments that that MAC address is hop to hop to hop. I'll come back to that in a little bit. So unless you have duplicate MAC addresses in the same on the same network or reachable by the same network, then you would have a problem. But otherwise, it's just region. So MAC address burned into each NIC, and they're all unique. You can view your MAC address by doing ipconfig all, typing ipconfig all at the Windows command, and here's the command at your Windows command prompt, type ipconfig all, and it shows you your MAC address, your physical address, the burned in address of your Ethernet adapter, your NIC card. And this one was built by Intel. I won't go into breaking it up, but I will say the first part, the first 6 hextets, the first 6 are the what's the word? The first 6 values represents the organization unit identifier, OUI, basically who makes the card. That's the first 6. And then the last 6 allows for the individual addressing, starting at 0000000000 and ending at FFFFFF. Remember, hex goes from 0 to F, 0 to 9, and then A, B, C, D, E, F. So that's your MAC address, and that's at layer 2 of the addressing on a computer, hop to hop to hop. We'll see it on the next slide, with the next 2 slides. Now, the IP address, IPv4, 32 bits, or IPv6, 128 bits. If you have IPv4, there's 4.3 billion addresses in the world. We're running out of them. Thanks to private addressing, we've been able to continue assigning IP addresses in IPv4. IPv6 has 340 undecillion addresses. It's enough. I already mentioned this. It's enough addresses to put an address on every grain of sand on the planet. It's another way of looking at it. But 340 undecillion addresses, 65,000 plus subnets of 18 quintillion addresses. This is the source destination address. Source and destination do not change, as I mentioned earlier. So this is what an IPv4 address looks like, and that's a subnet, by the way, 255.255.255.0. And I've already talked about subnetting, so that would double this presentation time if I went into it again. But you need both the network address and the subnet to be able to determine which network this IP address is in. The GUA, the global unique address, IPv4 address, is unique globally, and it can also FE80. This address is only unique locally. FE80 and local addressing is how IPv6 devices talk to each other within a network. But when you reach outside of the network, it always uses a global unicast address. The default gateway, that's how a device leaves the network. It needs to have a default gateway. Often the default gateway starts with FE80, ::1. In this case, it built its address itself by using the EUI64 method. Does that sound right? I think so. But anyways, you can tell it used it because of FFFE in the middle of that address, and it also flipped to 7th bit, but we wouldn't know that. But anyways, what is that? Let me make sure I got that right. I hope I said EUI64. That is what method it used here. Otherwise, it would just use a random number. And with 18 quintillion addresses, the chances are it's going to pick a unique address. By the way, that's only SLAAC. It's spelled SLAAC, stateless address auto configuration, SLAAC. They create their own addresses, IPv6. IPv4 has to be handed to you by a DHCP server. I'm getting way beyond what you need to know at this point in this course, so I'm going to keep moving. It's the danger of having a networking teacher teach an A+ class, because I always want you to spend I want to spend more time talking about the stuff you're going to need to know later. Anyways, so network addressing, the frame contains both the IP source and destination address and the source and destination MAC address. So in the frame, you have source and destination. Destination is the most important. It comes first. So destination and source MAC address, this is where it's going next. And so it comes first. And then source and destination IP address. If it's at the right place for the MAC address, then it's okay for source and destination to be reversed. But a device can communicate within a network just using its MAC address. But to leave the network and go outside, it has to have an IP address, someplace where it's going to. Think grandma's letter, right? So from post office to post office to post office, this is the MAC address. Here, we'll look at it here. Notice layer 2 MAC address changes all along the way. So this MAC address source, the router interface, MAC address destination. This interface source, that interface destination. This interface source, that interface destination, and finally gets where it's going. But notice as the MAC address changes hop to hop at layer 2, but layer 2, layer 3 stays the same. So source and IP destination remains the same. Your letter addressing that you sent to grandma's name is on it from the beginning until the end. Your name is in the top left-hand corner from the beginning until the end. And it doesn't change. It goes from post office to plane to truck to finally that guy walking down the street delivering her mail. And that is source IP and destination do not change. Layer 3 does not change. Layer 2 changes every time the post office gets another piece, sends it on its way towards the destination. Sometimes it takes 2 days, depending on the path it takes. Sometimes it takes 5 days. Sometimes it gets lost and it shows up by Easter. Your Christmas card gets to her at Easter in April. It happens because in IP that wouldn't happen because of hop limit or time to live, but it can route around the world a little bit before it actually gets to the destination. So anyways. IP addressing, I mentioned earlier, source and destination. There are 3 classes. We don't really use IP classes anymore. What you need to know is in Class A, there were a few networks of a lot of hosts, millions of IP addresses, and a few companies still have Class A addresses. Like I think Xerox has it. I heard recently Comcast has it. Has a Class A address. That means they have millions of addresses to be able to allocate. Class C, I'll jump down to the bottom, have millions of networks and only 256 addresses, right? And then in the middle, you have 65,000 networks of 65,000 addresses, 65,000 plus networks of 65,000 plus addresses. So depending on if we're using class full addressing, whatever you need. Do you need more networks or do you need more hosts? And you would decide. Again, we don't use that anymore thanks to subnetting. And we talked about subnetting a few weeks ago, and I have plenty of videos about subnetting on my channel. So if you want to get a review on subnetting, go look for my subnetting videos in my channel or out on the web with somebody else, and you will learn way more than you possibly thought you wanted to. Anyways, so here, these are 193.14150.0. This is an address and that's an address. The only way we know where it breaks down is with the subnet. They have not given us a subnet here, so there's no real way to know. This is 150 network and that's the 151 network, and it's probably a /24 or 255.255.255.0, but they don't give it to us. They're just showing you here that this network needs a router. Routers break up domains, so would be with the switch, and it would be broadcasting and all sorts of stuff going on here. Same thing over here. If we had one big domain, there's a better chance of things happening that would be bad. So you break it up into networks. This would be all admin. This would be all faculty, or this could be students, and this could be faculty, or this could be, well, this, you could set it up so all servers and all printers, however you want to break up your network, you can do it. But ultimately, you have to divide your network into smaller pieces. Now that is that for this week. 8 pages of the book I stretched out to an hour-long presentation, and I hope that's okay. I want to try to make sure you get something valid from me. If you don't go into network, you know a little bit more about networking. But if you do go into network, you will be ready when the teacher starts talking about breaking up networks and talking about layer 2 and layer 3, and all of that's very useful. So hopefully you find that information. Now, some of it is going to be on the A+ certification. And again, we're using the book by Cheryl A. Smith, Complete A+ Guide to IT Hardware and Software. And it is for the CompTIA A+ 2002-1001. I'm sorry, 220, 1001, and 220, 1002 certification exam. So make sure you're taking the time to go through these videos and take this class. Make sure you get that certification. Don't blow it off. Not that hard. Make it happen. Any questions? There's nobody with me, so you don't have any questions. But let me just close out the video without that screen. So again, my name's Don LaFon. It's been a pleasure teaching you a little bit more about A+ software today. If you have any questions and you're in my Netiquette, in my Canvas classroom, then please ask your questions in the help discussion forum. If you have questions and you're out watching my video on YouTube, please ask or comment. I love having comments down below, even if it's job well done or thank you or whatever. I love having comments down below, so please feel free to comment, ask questions, answer each other's questions. It's awesome when you do. Please like and subscribe. That helps other people find my videos, and hit that notification bell so you know when I release the next video. I'm working on these videos in the summer of 2022. So if you're watching them as I'm making them, welcome. And if you're watching them in the future, hopefully all my videos are good, and we'll see. I haven't made them yet. Anyways, my pleasure. Thank you so much for coming to class, and I will see you again in another week for the final portion of networking. Thank you for coming to class.